Hi everyone, it's Kira Garfolo with Greenville Tech's Math Department, and I'm teaching Math 109, Section 3.2 today, which focuses on solving quadratic equations. So remember in the last section, we talked about quadratic equations and what they were. The quadratic function has a parabola for a graph, and it can have up to two solutions, as we'll see. What does it mean, though, when we talk about a solution? Generally speaking, we are just finding the zeros of a quadratic function. We're going to talk today about several ways to solve quadratics in this section. The first is factoring, and factoring should be a review for you. You're going to set the equation equal to 0 and you're going to solve. So for example, if we have x squared minus 5x equals -6, we need to move that -6 to the other side so that all that is left on the right side is 0. So we're left with x squared minus 5x plus 6 equals 0. Then we can notice that 6 has factors of 2 and 3, which if we made it -2 and -3, they would add up to be -5. So we have x minus 3 times x minus 2 equals 0, and these are our factors. And setting each individual one equal to 0, we would have x equals 3 and x equals 2. Those are our solutions for this quadratic. Again, this should be a review, but if you need extra practice, there's some in your homework, and there are a ton of extra ones in your textbook in the extra homework sections. You can kind of see if you flip through the textbook, it even says, oh, solve by factoring. So you know those are actually solvable by factoring. Remember, not everything will factor nicely, so you want to stick to problems that actually tell you to factor. Now, let's give it another try. We want to solve this one by factoring. Take a minute, pause the video, make sure that you can work this out, and when you're ready, you can hit play. So if we want to solve this, we first need to move that 21 over to the other side. So we end up with x squared plus 4x minus 21 equals 0. 21, the factors that come to mind are 7 and 3. This is a minus, so one has to be positive and one has to be negative. This is a positive, so the bigger one has to be the positive one. So we have x plus 7 and x minus 3. So x plus 7 equals 0 would give us x equals -7, and x minus 3 equals 0 would give us x equals 3. So our two solutions here are x equals -7 and x equals 3. And we also have something called the square root method that works in certain cases if our equation looks a certain way. So it has to look like one of these two below, or it can be converted to look like that. So you can have the quantity ax plus b squared equals some number, or you can have just x squared equals some number. Since this whole quantity on the left is squared, if you take the square root, your answer on both sides, that'll just turn into ax plus b, and over here it'll be plus or minus the square root of c. The right side is even simpler because you take the square root, and so it's just x equals plus or minus the square root of c. Let's look at an example. Looking at this with the square root method, we have 2x squared minus 16 equals 0. So first we need to move that 16 over to the other side. So we have 2x squared equals 16. Now that's still not quite what we need because we need that x to go on its own. That 2 needs to go away. So we'll divide everything by 2 to get x squared equals 8. Now we know that if we take the square root of both sides, we'll have x equals plus or minus the square root of 8. And we can further simplify that. So x equals plus or minus the square root of 8, which we know there's a perfect square of 4 in there, so it's plus or minus 2 times the square root of 2. These are two answers here because we have 2 square root of 2 as x and -2 square root of 2 as x. So we get the two solutions with one little formula. Now, sometimes we have to suck it up and do it the ugly way that nobody seems to like. It's really not that bad. You've probably seen it in another class, but we have something called the quadratic formula. And we can solve any quadratic equation with the quadratic formula. And it always, always works. It'll work for ugly equations, and it'll even work for complex roots, which the other methods typically do not, at least not nearly as easily. If you have complex roots, it's definitely the easiest route to take with the quadratic formula. The quadratic formula is x equals negative b plus or minus the square root of b squared minus 4ac, all of that divided by 2a. Now, if you plug this into your calculator, be very, very careful with order of operations. You may even want to do it in a series of steps, but you want to be very careful that you don't make any order of operations mistakes because it'll throw your entire answer off. Let's consider an example, and it's not a very pretty example. So the national healthcare expenditures in the US from 1980 onward are modeled by this equation, 2.224x squared minus 21.841 plus 353.3. Here, x is the number of years after 1970, and c of x is measured in billions of dollars. So that's a 2.224 billion. At the end is $353.3 billion. We want to estimate the year after 1970 when the expenditures will reach $5,227 billion. So we first need to set our c of x equal to that 5227. So our value here equals that whole equation that we had. Now to use the quadratic formula, we can't use it just quite yet. We need to move everything over to one side. So that 5227 has to be subtracted away and moved over here. So we get 0 equals 2.224x squared minus 29.841 minus 4873.7. I believe that there's an x there, is there not? I have missed an x. I apologize, guys. There's an x right here and right here. I will have to go back and correct that. So here A is 2.224, B is negative 29.841, and C is negative 4873.7. Again, there is an x right here and an x right here. So now you try the quadratic formula using A, B, and C that we just found. Pause your screen, work it out, and come back and press play when you have an answer. So if we look at our work here, remember we're dealing with negative b plus or minus the square root of b squared minus 4ac all over 2a. And now it's just kind of a plug and chug, but it's a very careful plug and chug. Here's b, negative b because b was already negative, so it drops to be a positive, plus or minus the square root of, here's b squared, minus 4 times a times c, all over 2 times a. Now we use our calculator and we get this all simplified out here. And we end up with 29.841 plus or minus 210.341 divided by 4.448. Remember that plus or minus means one time we're going to do plus and the other time we're going to do minus. So one value of x will be with the plus and another value of the x will be with the minus. So we get x equals 54 and x equals negative 40.6. Now in this setting, we're talking about the year after 1970. So it doesn't make sense. You're talking here about 54 years after that it's going to reach that expenditure. Here you're talking about 40 something years before, which doesn't make sense. So this one we're going to kind of throw out and we're going to focus on the 54 as our viable answer. So 54 years after after 1970 is going to give us 2024, which isn't too far up the road, and I would imagine it's not terribly far off if we're not already there. So if you didn't get the right answer, take a minute, find your mistake, try again, and make sure you can do it from a blank start to get the correct answer. Now there's also one other method that we're going to talk about called completing the square. And completing the square is something that you can do with pretty much any quadratic. I don't want to say any quadratic. You can do it with a lot of them. The textbook and the homework will tell you, hey, use completing the square. So let's look at an example, because instead of working with symbols, this one really makes more sense to talk about in terms of an example. So we're going to use x squared minus 12x plus 7 equals 0. There's nothing that we can just immediately square to get this to work out, which is sad. It'd be nice if we could. So instead, we're going to move that 7 way back over here to have x squared minus 12x equals minus 7. Now this right here is promising because we can make it to where we can make this a perfect square. X minus something squared would equal this. But if we need to add something to here to make that work, we also have to add it to the other side, because otherwise we're going to alter the value. But remember, if we do it to both sides equivalently, it will remain the same value. It turns out what we need to add is half of this number squared. So even if it's negative, it's going to be positive because you're going to square it. So you're going to add half of this squared. So in this case, half of 12 or half of negative 12 is going to be 6 or negative 6. It doesn't matter. And squaring that is going to be 36. So you're going to add 36 here and you're going to add 36 here. So you'll end up with x squared minus 12x plus 36 equals negative 7 plus 36. Now, if we look here, this is a perfect square on our left side. So x squared minus 12x plus 36 simplifies to x minus 6 squared. And negative 7 plus 36 turns into 29. Now we can use the square root method that we already learned about a few slides back to give us x minus 6 has to equal plus or minus the square root of 29. We move that 6 over to get x equals 6 plus or minus the square root of 29. So those are our two values of x, 6 plus the square root of 29 and 6 minus the square root of 29. 29 is a prime number. It doesn't factor any more than that. Now it's time for you to try. Apply the same reasoning, but complete the square to solve this one. Again, pause your screen, give it a few moments, and when you're ready with your solution, hit play. Okay, so the first thing you're going to need to do is move that 9 over because you see that this is not a perfect square. So we say x squared minus 4x equals 9. And then we need to add half of this squared. So half of 4 or half of negative 4, 2 or negative 2, doesn't matter because you're going to square it. So you're going to add 4 because 2 squared is 4 to both sides. So now we see that this quantity right here is a perfect square. And 9 plus 4 is 13. So we end up with x minus 2 squared equals 13. Using the square root method now, we have x minus 2 equals plus or minus the square root of 13. Move that 2 over and we get x is 2 plus the square root of 13 and x is 2 minus the square root of 13. Now on your test, you're welcome to write x plus or 2 plus the square root of 13 and 2 minus the square root of 13. But just the way I have it circled there is sufficient. That is two different numbers. The graphical method is presented in this section, but we're not going to actually spend much time on it because you already know how to do it. You're going to graph f of x in your calculator, and you're going to use that zero feature to find the zeros. These are your solutions. Again, make sure you pay attention, and if there's some context, like a realistic word problem, like where we saw the healthcare expenditures, the negative value didn't make sense, but the positive did, so we only kept the positive. You want to be very careful. You have to move before you put y equals, make sure that you move everything over to one side so that you have, x squared plus something x plus something equals 0. If you don't have equals 0, you're going to get the wrong answer when you find the zeros, because the whole point is you're finding where it equals 0. So if you think back to what we did in the previous section here, we had graphed the pumpkin throwing path. And when we found that 0 right there, that was a solution to our equation. X equals 3.434. That was one value of x that solved it. We could do 0 over here to find the other solution if we wanted, using the same exact 0 feature. Okay, so pretty much everything we've seen so far has two different zeros. And quadratic functions can have as many as two zeros, but they can also have 0, 1, or 2 real roots. Okay, so there's always two roots, but sometimes they're imaginary. So if you're looking at a graph, you can see three different cases. In this first case, we see a parabola that hits the x-intercept or the x-axis twice, so it has two x-intercepts or two zeros. Those are your two real roots. In this case, it crosses that x-axis twice, has two real solutions, and you can use really any of the methods that we've talked about today to solve. Another case is where your parabola touches but doesn't cross. It kind of kisses that x-axis, right? It's sitting right on it. In this case, you do have a real root, but you only have one of them, and it is multiplicity 2, which means that it comes from something squared. So that root is there twice. To solve this one, you can use all the same methods that we just did. Just like before, you can use factoring if that applies. You can graph, you can complete the square, you can use square root method, whatever to get your answer. And the third case is one of the more unique ones, and it is where you don't cross the x-axis at all. It's either floating entirely above or flipped over entirely below that x-axis, and it never crosses, never touches. It goes off to infinity. In this case, our equation has no real solutions because it doesn't have any x-intercepts. And in that case, you almost always have to use the quadratic formula, and you'll verify that your solutions are not real. You cannot solve this one using the graphical method on your calculator because there's no zero to look into. Now we can use something called the discriminant to tell us how many of those real zeros we have. And the discriminant, if we have it in standard form of ax squared plus bx plus c equals 0, then b squared minus 4ac is going to be our discriminant. Notice if you go back to the quadratic formula, this b squared minus 4ac is everything that's under that square root. So if our discriminant is positive, then we know we have two real solutions, and you can use really whatever method you want to use. If your discriminant is exactly equal to 0, then you have that multiplicity of 2 situation where it's going to kiss right against that x-axis but not cross it. And in that case, you can still use any method because there's only one real solution. But it's real nonetheless. It gets tricky when your discriminant is negative. So when your discriminant is less than 0, then it never touches, never crosses that x-axis. It has no x-intercepts whatsoever. So it has two solutions, but they're both not real. In this case, the best course of action is going to be to use the quadratic formula. Let's use the discriminant in an example. So let's say that we want to find all solutions to x squared equals negative 2x minus 3. Now remember, the first thing we need to do is have everything on one side of the equation or the other. So here we're going to move it all to the left side. So we'll end up with x squared plus 2x plus 3 equals 0. If you had moved it to the other side, no harm, no foul. Your signs will all be opposite, but they'll all balance themselves out. So here, a equals 1, b equals 2, and c equals 3 in the ax squared plus bx plus c standard form. The discriminant, remember, is b squared minus 4ac. So when we find that discriminant, we get 2 squared minus 4 times 1 times 3, which if we work out, it's going to give us negative 8. So since our discriminant is not positive or 0, it is negative. That means that we have two complex roots. We have no real roots. In this case, we're going to need to use the quadratic formula to find the roots. So now you're going to give that a try. So remember that we wanted to find the roots of x squared plus 2x plus 3 equals 0, and you want to use the quadratic formula. Pause this video for a minute, give it a try on your own, and when you have it worked out, go ahead and hit play, and you can check your answer, find any mistakes, verify that you knew what you were doing, whatever you need to do. So if we work it out here, Here's our quadratic formula. When we plug in b squared 4ac over 2a, this is really just plug and chug, right? You're going to get a negative value under here. We already know that that discriminant is a -8. So right here, mathematically is correct, but it's not in proper format. We need to simplify that square root of -8. We need to pull the I out, and we see that there's a perfect square of 4 in there. So we can simplify square root of -8 as the square root of -1 times 4 times 2. We'll pull the -1 out as I. We'll pull the 4 out as the 2 because square root of 4 is 2. And we'll leave the square root of 2 there because there's not much else we can simplify. We end up with -2 plus or minus 2i square root of 2 all over 2. Now notice here that 2 is everywhere, so we can simplify it to just -1 plus or minus I times the square root of 2. So your two imaginary roots, your two complex roots here are -1 plus I square root of 2 and -1 minus I square root of 2. You can't exactly graph those because they're imaginary, so the graphical method wouldn't help. So in conclusion, there are a lot of ways to solve quadratic equations, and often you're going to be able to use multiple ways to get the right answer. I would encourage you, where your homework tells you to use a certain method, to go ahead and use it, because if your test asks you for a certain method, you're going to want to be familiar with it. And remember that not all methods always work. Sometimes they lend themselves one way or the other. When all else fails, especially when that discriminant is negative, the quadratic formula is the way to go. You can't even graph it and get your zeros if they're complex or imaginary because they don't ever cross the x-axis, and we cannot visualize that in our technology. If you do these correctly, you're going to get the same answer no matter what method you choose. So it can be a great way to check your work, even if you don't end up using your preferred based on the way that the homework tells you to do it. Remember, if you're struggling, this is a very heavy, very intense unit. And so make sure that you get the help that you need. You can go to the Math Center. There are a ton of resources available within our Blackboard shell. You can come see me or email me. We can meet during office hours. Lots of resources at your disposal. Thanks for tuning in. I hope you guys have a great day, and I hope to see you next time.